In this video, you're going to be introduced to the idea of a neutralization reaction between a base and either a strong or a weak acid. We are going to compare the neutralization of a base with a strong acid to the neutralization of a base with a weak acid and see how they're similar and how they're different. Before this video, you should have already seen the milk of magnesia demo. In that demo, we took milk of magnesia, which is magnesium hydroxide, and we added either hydrochloric acid or acetic acid to two exactly the same containers of magnesium hydroxide. The acid neutralized the magnesium hydroxide base, and we knew that magnesium hydroxide was neutralized when the solution began to appear clear. Based on that demonstration, both hydrochloric acid and acetic acid neutralized with the same neutralizing ability. In other words, it took the same amount of 3 molar hydrochloric acid as it did 3 molar acetic acid to neutralize the same amount of magnesium hydroxide. So it seems that it doesn't matter if something is a weak or a strong acid, both neutralize the base with the same effectiveness. So first, it says, why will adding an acid cause magnesium hydroxide to dissolve? And by dissolving, that's what made the solution appear clear. Well, if we look at this, magnesium hydroxide, while it is considered a strong base, it is not very soluble. So we use this double arrow to denote that there's an equilibrium between solid magnesium hydroxide, that's what appears cloudy in the solution, and the dissolved ions. So what we saw is that as we added HCl, we know that we're basically adding H+. Or when we add the acetic acid, we're adding H+. And we know that there's always an equilibrium between hydronium, or the hydrogen ion, and hydroxide. So as we add acid, this causes the concentration of hydroxide that's in the water to drop. And when the concentration of hydroxide that's in the water drops, that causes this equilibrium to move forward at a faster rate in the forward direction to replace that dissolved hydroxide in the water. Eventually, all the cloudy solid magnesium hydroxide goes away and the solution appears clear. Now it says, what is happening when the system changes color and then returns to blue, which would be basic again? Well, what happens, first you dump in the acid. And as soon as the acid goes in there, the H+ concentration skyrockets because you just dumped a whole bunch in. But then the magnesium hydroxide, that was the cloudiness, it breaks up into the magnesium 2+ ion and the hydroxide ion in response. And as more and more magnesium hydroxide dissolves, more and more hydroxide gets in the water, and then that reacts and uses up some of the hydronium in the water. So it returns to more of a basic condition. You saw that change happen really quickly when we added HCl. When we added HCl, it turned like orange or pink right away, but then quickly cycled back through the colors to get back to blue again as the magnesium hydroxide dissolved. On the other hand, when we added the acetic acid, we saw it turn pinkish red, and then it took a little bit of time, but it eventually got back to the same basic color again. So we saw that it was faster with the strong acid, and it was a little bit slower with the weak acid to return to equilibrium. The reason for this difference in speed is because as soon as we put in HCl, you immediately get H+. Where when we put in, and you get all the H+ right away. On the other hand, with the weak acid, when you put it in, you get a little bit of H+, but you have to gradually, like, a little bit of H+ comes off the acetic acid and reacts with hydroxide. Then, as that H+ gets used up, then a little bit more acetic acid will lose its H, and then the H again, you'll have the neutralization of hydronium and hydroxide. Then a little bit more acetic acid loses its H. So it's a process of the H is removed from the acetic acid slowly, because acetic acid is a weak acid. So just some, you'll take off a little bit at a time. Although the speed of neutralization is different, the amount of acid needed to do the neutralization is exactly the same. So the strong hydrochloric acid and weak acetic acid both worked equally well to neutralize magnesium hydroxide, and we're going to explore why. So we already know that for the autoionization of water, the process of water ionizing into hydroxide and hydronium, we know that the equilibrium constant for that, which is given the value or the special name Kw, is 1 times 10 to the negative 14th. If we take that system and we flip it around so the products become reactants and the reactants become products, K is products of reactants, so if we flip their places, we get the reciprocal of Kw, 1 over 1 times 10 to the negative 14th, which is 1 times 10 to the positive 14th. We go from a very small K to, when we're making water, a huge K. If we do one more adjustment and we double all of the coefficients in that second equation, so instead of having 1 hydroxide and 1 hydronium, we have 2 hydroxide, 2 hydronium, and 2 water, then we would square that K value, which gives us 1 times 10 to the 28th, an even bigger K value. And we're going to use that and see where that comes into play on the next couple slides. On this slide, we're going to look at all the systems, all the reactions that are in play in the beaker in our demo where strong hydrochloric acid is being added. In this demo, we have the magnesium hydroxide solid ionizing into magnesium ions and hydroxide ions. And we put a double arrow there because magnesium hydroxide is not very soluble in water. So only a small percentage of it actually breaks up from the solid and ionizes. That's indicated by the fact that the K value for this process is really pretty small. The second system is hydrochloric acid ionizing to be hydrogen and chloride ions. Now that we use a one-way arrow because by definition the strong acid ionizes completely, and we get a K that's huge, so big it's not even tabulated. And then we have the third system or equilibrium process that's happening here is hydroxide and hydronium that come from, the hydroxide comes from magnesium hydroxide, the hydrogen or hydronium comes from the HCl, and those things, as they're available in the water, they will react and become water. And that K value, as we saw in the previous slide, is 1 times 10 to the 28th. So that's a big, big value. So if we add all of that together, what's essentially happening here is that the magnesium hydroxide solid is being neutralized by the acid that we are adding to make magnesium ions and water. And since we are adding up 3 processes, we multiply the K values. So if we multiply 10 times the negative 11th times 10 to the 28th, that gives us 10 to the 17th. That's really big just in and of itself. But we have 10 to the 17th times some other really, really big number from the K for the hydrochloric acid. So what we say is, because this K is going to be a huge number, some huge number times another huge number, we can really consider this reaction not to be equilibrium with a double arrow, but really to be a one-way reaction that's going to employ stoichiometry. It's because the K is so big that we essentially have all products when the process is complete. We're going to do the same kind of analysis, but for the weak acetic acid. Again, the things that are happening in here are magnesium hydroxide ionizing, same Kw we saw, or Ksp that we saw in the previous slide. We've got weak acetic acid. This is the different step in equilibrium with hydrogen ions and the acetate ion. The K value for that process is 1.8 times 10 to the negative fifth, but we're squaring it because I doubled all the coefficients here. Then we take the hydroxide from the first system and the hydronium from the second system, and they combine to make water. And as we discussed before, the K for that process is 1 times 10 to the positive 28th. So if we combine all of those systems, we get this overall reaction that acetic acid and magnesium hydroxide are neutralized to make magnesium ion, acetate ion, so magnesium acetate, and water. And if we take our 3K values, 10 to the negative 11th, 10 to the negative 10th, and 10 to the 28th, and we multiply those all together, the coefficients will add. We get 10 to the negative 11th times 10 to basically the negative 10th times 10 to the positive 28th. K is going to be on the order of 10 to the 7th. That is still a pretty big K. So just no different actually than the hydrochloric acid, because the K is 10 to a pretty decent sized positive number. We really can think about this neutralization reaction as going to completion. Even though it's a weak acid with a strong base, even here, because we are forming water, which has such a big equilibrium concentration, there's so much more water present than hydronium hydroxide. If water is one of the products, you're going to have a reaction that goes to completion. So to summarize what we have learned from this milk of magnesia demo, first, weak acids are really only weak in relation to other weak acids. So you can compare like which weak acid is weaker, which is stronger. And second very important point, if the equilibrium constant for a process is much, much bigger than 1, so you've got 10 to a positive, really if K is bigger than 1,000, so K is bigger than like 10 to the third, that's really pretty big, then we're really not talking about equilibrium anymore. We're talking about limiting reactant and stoichiometry tools and BCA tables instead of ice tables and molarity and reaching equilibrium. And really and truly, as we get further in chemistry, stoichiometry and equilibrium are similar things, but they're opposite ends of a continuum. The most important point we've learned from this demo is that if a neutralization reaction makes water, the acid-base neutralization reaction will go to completion. Because of that huge K value for the combination of hydronium and hydroxide to make water. So it's because of K being 1 times 10 to the positive 14th or 28th, depending on how you write the coefficients. So anytime we are making water, we are going to be talking about stoichiometry, about one-way arrows, and about limiting reactants.